In our last lectures on Monday, we introduced you to the concept of PE-pH diagrams. PE-pH diagrams are diagram picture representations of the PE-pH expressions that we derived from the Nernst equation on Monday. And what we can do is we can use a PE-pH diagram to make a prediction about the most stable form, the speciation, of any chemical that we might be interested in under specific potential, PE, and acid-base, pH conditions. We saw that the PE-pH diagram is a diagram with PE on the y-axis, the negative log of your electron activity, and pH on the x-axis, the negative log of your proton concentration. PE-pH diagrams are drawn for chemical species related to a specific element, and they show you how the speciation of that element changes as the pH of the solution and the potential of the solution changes. So they can summarize not only acid-base reactivity for a chemical compound, but also redox chemistry for a compound. Last time we looked at the PE-pH diagram of iron, and here we want to look at the PE-pH diagram of nitrogen and show you how the diagram is related to the PE-pH expression. So if we look at the PE-pH diagram of nitrogen, not surprisingly, we see that more oxidized forms of nitrogen, nitrate and nitrite, predominate at higher solution potentials, where in nitrate, nitrogen is in the +5 oxidation state. In nitrite, nitrogen is in the +3 oxidation state. More reduced forms of nitrogen, ammonium at lower pH, and ammonia, the base, at higher pH, show up at lower PE values where the water would be more reducing. We can summarize one of the fundamental transitions that's a redox change between nitrate, NO3-, and ammonium, NH4+, using a balanced 1 electron reduction half reaction, which would say that 1/8 of a mole of nitrate plus 5/4 of a mole of protons plus an electron goes to 1/8 of a mole of ammonium and 3/8 of a mole of water. We can derive the PE-pH expression that describes the reduction of nitrate to ammonium by remembering that the basic form will follow the Nernst equation, and that the PE, the electron activity under non-standard conditions, is equal to PE0, the electron activity under standard conditions, minus the log of the reaction quotient Q. So we're going to have products on top, reactants on the bottom, everything raised to their stoichiometric coefficients. Only the electron doesn't appear in the reaction quotient. Our expression now says that the PE, the negative log of the electron activity, is equal to 14.15 minus the log of the proton concentration to the 5/4 minus the log of the ammonium concentration to the 1/8 divided by the concentration of nitrate raised to the 1/8. We can simplify this expression further and say that the negative log of the proton concentration to the 5/4 is the same as 5/4 times the pH, because pH is the negative log of the proton concentration. And we can similarly simplify the last term by remembering that for logs, if each of these terms in the parentheses is raised to the 1/8, we can pull the 1/8 out in front, and we have just negative 1/8 times the log of the ammonium concentration divided by the nitrate concentration. The way the PE-pH expressions relate to the PE-pH diagram is that these mathematical expressions describe the slope of the lines that separate the relevant species participating in a chemical reaction. So if we're interested in the reduction of nitrate to ammonium, this PE-pH expression we've just generated describes the slope of the boundary separating nitrate and ammonium. So this expression would describe this boundary here, and we could derive a separate expression relating the PE value to the concentration of nitrate and nitrite, or nitrite and ammonium. So these equations that we generated last time are the equations for the boundaries that separate the predominance areas on the PE-pH diagram.